Carl Hibbitts, and he'll be telling us about characterizing water on airless bodies from vacuum UV and IR measurements.
Thanks, Paul. Thanks, everybody, for sticking around for the last talk. So this is a laboratory talk where we'll be speaking about one of the three topics that I'm researching as part of this survey. Work that we're doing, it folds in nicely to the other topics, which one of them, Michael Poston over there, can talk to you quite a bit about, which is temperature-programmed desorption of water from soils. We're looking at the spectral characteristics of adsorbed waters on these soils, both in the mid-infrared, which is around 3 microns, and in the ultraviolet. The concept is to understand what do these soils look like when they're not under terrestrial conditions, but as it baked out under vacuum, as you'll find them on asteroids or in the moon. That also leads a little bit into, or quite well into, some effort led by Andy Rifkin, where he is attempting to use a modified Gaussian model to remove this spectral signature at 3 microns from terrestrial measurements to derive analytically what the spectrum would look like desiccated on asteroids or on the moon. Anyway, with about 11 minutes left, let's move on. I should have actually asked you how this works. Okay. All right. So let's start with some squiggly lines right off the bat to explain what we're working with. This is Spectra from 1987, the Wagner et al. Document that most people refer to in looking at the reflection spectrum, the UV, comparing magnesium olivine to iron-rich olivine. You can see there is besides 1 micron band due to crystal field transition, you have oxygen-metal transfer, charge transfer here. Iron-rich, it gets darker more quickly. Okay. As we'll see later, there's also effects due to, potentially, there is effects due to water ice, and the question is, does OH also have an effect in the spectral region? Okay. This effect, as I just mentioned, comes from the charge transfer between metal and oxygen. Around 350 nanometers, charge transfer between calcium, magnesium, or even better, iron and titanium and oxygen. Induced bands around 350 nanometers, 200 nanometers, around there. That's due to the presence of these network modifiers, calcium, sodium, and potassium, shown here, and here for typical silica. And these are the oxygens. The charge transfer between non-bridging oxygens and these network modifiers tend to be, that absorption band tends to be around 160 nanometers out to 250 nanometers, potentially even longer. Whereas the charge transfer between the bridging oxygens, this tend to be shorter, higher energy. Okay. All right. And also showing some hydrogen adsorbed onto there as if OH would exist. So we have taken measurements in our laboratory of water, well, not exactly water-free. These are glasses produced at Corning under water-free conditions, but they are now powders, and they could have adsorbed water on them. So the point here is to show you that we're able to actually obtain vacuum UV through visible spectra and bidirectional reflectance for these materials, iron-free glass, anorthite, and this is the iron-related oxygen-metal charge transfer band. And this is the, here below 200 nanometers, is the charge transfer band due to the network modifiers in oxygen. This one is a iron-free glass, so the question is, why does this band continue to remain? There may be a small amount of iron there. We have to understand this a little bit more. You can see water frost is a very diagnostic band here at 170, 180 nanometers. Question we have posed is, does this band also exist for OH? For adsorbed or even for absorbed molecular water on these materials or not? Is this a way to identify adsorbed water at the poles of the moon or in asteroids where there's not enough perhaps illumination? Look at the 3 micron region. So what we did in laboratories make measurements both at 3 microns and here in UV for samples under the same conditions, both before they were baked out to remove all water or as much as we can and afterwards. Okay. And the motivation, as I said, is to understand if we can use the UV to not only look for water ice on the poles, which is an example of possibly that being done so with LAMP data, showing the brightness differences here at 160 nanometers versus about 180 nanometers, where you're in the band where it's dark and then where it's brighter here, where the water ice is brighter as well. Does the same phenomenon exist for OH or for adsorbed water or not? Okay. Potentially, this could be applied to Vesta. This could be applied anywhere, as I said, where there's not enough illumination to use the reflectance at 3 microns. Okay. But speaking of reflectance 3 microns, it is a very powerful diagnostic tool for not only identifying the presence of adsorbed water, but also for identifying water ice. In this case, we're looking at adsorbed water. These are spectra from Takir et al. 2013 and taken with our laboratory facility, comparing materials under, let's see, ambient conditions. That means terrestrial conditions exposed to Earth's atmosphere. And then after baking out and removing some of the adsorbed water, you can see the 3 micron band here goes away to some extent. Some of it remains, did not bake out long enough, or the partial pressure or the pressure in the chamber was a little bit high on the water reabsorbed. In actuality, we find out that even if we're at 10 to minus 9 torrs and we bake out at 100 degrees C overnight, a lot of OH remains on the surface. Okay, remains adsorbed, so it's very strongly stuck. A lot, though, is still being sub-monolayer, so a fraction of a layer of OH remains on the surface, but because it's particulate and there's a lot of optical path at 3 microns through this material, it's sensitive to these small amounts of OH or water. You can see it works for the different materials. Ivuna, being a CI, absorbs a whole lot of molecular water here, diagnostic, 2.95 micron band, and it goes away. You only have the OH left. Okay. So again, as you've seen before, there are spectra of the moon showing a band potentially, or a band at 2.8 or even 3 microns. Can we detect this at UV wavelength or not? This is something we can use a lamp for or other missions for. Well, that's why we made these laboratory measurements I'll show later. Again, this could apply to asteroids as well. There's a UV spectrometer taken with you. You can use that information to corroborate or even look for, with a different technique, this water on these surfaces. Again, not a whole lot of water ice, but small amounts of adsorbed water, which may be present at the 10, 20 to 100 ppm level. Okay. All right, so this is the system we use in the laboratory, which has a UHV chamber here. This is a monochromator that is under vacuum that operates from about 150 nanometers to 550 or 570 nanometers in reflectance, and this is the FTIR. This allows us to obtain both IR and UV reflectance spectra of a sample not at the same time, but under the same conditions. We have to rotate the sample between the measurements. This is path links for the UV, showing it reflecting off the sample and detecting by the PMT. And the IR, which is reflecting off the sample, being collected by the MCT detector, liquid nitrogen cooled. So let's go through some spectra real quickly. About 4 minutes, perfect. So under ambient conditions, there's a 3 micron band. This is olivine, 1 micron band in olivine, 3 micron bands due to adsorbed water. This is contaminant, organic contaminant. You should ignore that. Under initial vacuum, put it in the vacuum chamber and pump out, immediately take some spectra, and the weakly adsorbed molecular water goes away. More strongly bound molecular water or OH remains adsorbed. After baking out overnight at 100 degrees C, you desorb some of the remaining, or probably all the remaining molecular H2O with OH remaining, most likely, as shown here with this band. These are not scaled together. This shows you the, I guess, fidelity of the measurements not. Okay. So we saw that in IR, and we see that the band position even shifts adsorbed water to most likely OH internal or adsorbed OH as well. This being San Carlos olivine, there's a lot of internal OH in it as well, so we aren't sure which this is due to. This also relates to the work by Andy Rifkin, that potentially we can model out this. If that's the only spectrum we have, we can well characterize this effect, and we can mathematically derive this without actually having to measure that in the laboratory, because this takes 1 to 2 days to make this measurement. It's not a very quick process to derive the spectra of materials under vacuum and baked out. So we see a difference when you pull vacuum on a sample, the water goes away. However, in the infrared, what we have for olivine, again, San Carlos olivine, it is iron poor, so it does not have a strong OMCT band here. It has a typical band here that dies off there. This is the initial vacuum, so most or all of the H2O is already gone. Being vacuum UV measurements, we cannot take ambient spectra of this. All these spectra have to be done under vacuum conditions. So we can't look at large amounts of adsorbed H2O. So this is partially desiccated, and after fully desiccating overnight, what we end up with is the same spectrum. So we will see consistently for the 3 examples I'm going to fly through in the next 1 minute that the infrared is very good at detecting desiccation or small amounts of OH or adsorbed H2O, whereas UV is not affected by OH. UV is sensitive to water ice, as we know, has a very strong signature, but there's apparently no signature of adsorbed OH or perhaps even adsorbed H2O in the UV. Okay, so move on. So that was olivine, which is a, okay, silicate. This is a iron-free glass which has no internal water in it, and of course should have no iron in it. And there we go. It does. This band, of course, changes as you desiccate it in UV, and it changes position as expected as you go from water to adsorbed OH. In the UV, the band position does not change at all, as shown here. Typically in the UV for iron-free materials, there's not as strong of a charge transfer band. It's bright out here, and this band is shifted to this wavelength. We've demonstrated that earlier. And everything is dark out here in the UV for all the silicates we look at, again, to the charge transfer between probably the silicon and the oxygen, or the aluminum and oxygen. Okay. Now for the Instantite, same result, baking out, removes much of it. Again, these are spectral features again. In the IR, the band shifts again. In UV, no effect. So I have a very simple one point to make here, is that UV is not sensitive to adsorbed water. And that was a question we've always had for quite some time. UV is very good at detecting water ice. IR can detect adsorbed water as well, but UV will not be sensitive to adsorbed water. And here's our conclusions. And this is my timer, trying to keep myself to the same time as everyone else. All right. So here we go. I just summarized this already, and you can read it for yourself. The reason the UV may not be sensitive to OH is that it implies that the 2s to 2p orbital transitions responsible for that band water ice may not occur for the OH, or the shift is such short wavelength, short wave of 160 nanometers, that they are obscured by the OMCT transitions already present between the silicon and the oxygen. Okay, thank you. Any questions?
Questions? Amanda.
Hi, Amanda Hendricks from PSI. So this is interesting, right? Because with the LAMP instrument on LRO, we do detect that 160 nanometer absorption edge, and even at low latitudes, right? Diurnally varying. And we said that we didn't know if it was OH or adsorbed water or water frost.
Mm-hmm.
But if you don't think that the UV can detect OH or adsorbed water, then that says something about those LAMP results.
That's what the experiments show. That is not sensitive at all to OH. Okay, or perhaps low levels of adsorbed H2O that's very strongly stuck. So that's
and
what
that's
I would
because
conclude.
the OH wouldn't stay stuck onto the molecule in vacuum.
Well, as work by Michael Poston has showed, OH can, or maybe H2O. Don't know about OH. Your work, the TPD work, is H2O. There's a very small amount that can stick on at warm temperatures around 400 Kelvin, but you know that's over a short time. So my feeling, our feeling is that I don't think any H2O is going to be present on the illuminated terrain. That it could be submonolayers of OH, very strongly adsorbed. Okay. Or more likely, you know, we're seeing implanted protons that look like OH. That Larry Teller and his postdoc have shown that that can be produced in the lab as well, OH band through implantation with protons.
I don't know if that explains the UV signature.
Hmm?
I don't think that explains the UV signature.
No, I don't either.
Right. Okay.
No.
Okay.
I don't think OH would explain the UV signature.